In 1810, nearly a decade after Thomas Young's demonstration of light interference, a French physicist named Étienne Louis Malus observed another curious property of light, which he named polarization. This property manifests when light is passed through certain materials, usually types of crystals, which reduce the intensity of the outgoing light. This is how sunglasses work, for instance. As with Young, Malus's original experiments are tricky to convey. It is much simpler to use modern demonstrations and equipment. Thus, we procure a beam of sunlight and several sheets of Polaroid filter. For now, it is not important how exactly these sheets, these polarizing filters, filter light on the microscopic level. We only need to observe a few curious facts about how they affect light macroscopically. So, we have ourselves a beam of sunlight shining, say, through a hole in a concrete wall into a dark cell. We now place one of the Polaroid sheets in the way of the beam. We observe that the outgoing beam, having passed through the filter, is reduced in intensity by about 50%. From this, we might conclude that the Polaroid sheet is just a semi-transparent material, which absorbs or deflects 50% of the light and lets the other 50% through. However, we now place another Polaroid sheet in the way of the beam. To help keep things straight, let's label the sheets. The first sheet we used is A, while this second sheet we've introduced is B. We place B after A so that B filters the beam which was already filtered by A. We also hold B at the same angle as A, so that the sheets could stack neatly on top of each other. Now, if A and B were simply semi-transparent materials, we should expect B to repeat what A did, namely, reduce the intensity of the light by another 50%, so that the final beam would be only 25% of its original intensity. But this is not what happens. Instead, B does little, if anything, to reduce the intensity of the light any further. It is as though B were fully transparent. Well, perhaps we made a mistake. Maybe sheet B isn't really the same material as sheet A, they just look similar. So we swap the order of the sheets. Now the light hits B first, and then it hits A. But this doesn't make a difference. When we put B into the beam first, it reduces the light by 50%, just as A did before. Moreover, when we place A behind B at the same angle, A likewise fails to filter the light. The final beam is still 50%. From this, it is evident that the sheets are not just semi-transparent materials. Rather, they seem to imbue light with additional properties, such that when the filtered light encounters a second filter, it will behave differently than it did with the original filter. In Malus's terms, the first filter has polarized the light. What exactly does this trait of polarization involve? Well, let's experiment some more. So far, we've only held A and B at the same angle, so that they stack neatly. But what happens if we rotate one of them, so that the angle between them is different? For instance, take the scenario where A is first and B is second. As we rotate B, now more and more light is filtered out. B is becoming, relative to the light, more and more opaque. What if we rotate A instead? The same thing. A will filter the light by 50% no matter what angle it is held at, but the amount of light that passes through B which we weren't rotating, will change. The opacity of the second sheet depends upon its angle relative to the first sheet. In other words, what matters is not the angle of the individual filters, but rather the difference in angle between them. When A minus B equals 0 degrees, that is, when they are at the same angle as each other, then the light is reduced by 0%, just as we saw before. That is, A reduces it by 50%, but B reduces it by 0%. But when A minus B equals 30 degrees, the light is reduced by B by 25%. At 45 degrees, it is reduced by 50%. At 60 degrees, by 75%. And at 90 degrees, 100% of the light is shut out by filter B. After that, as you continue to turn filter B or filter A, the process simply reverses until you reach 180 degrees, where it returns to 0% again. The point is, when the filters are aligned perpendicularly to each other, we have 100% light reduction. But when the filters are aligned parallel to each other, we have 0% light reduction. And we can graph the percentages of reduction around a circle. The first sheet simply polarizes the sunlight at a cost of reducing it by 50%, regardless of the angle it is held at, and assuming that the sunlight has not been polarized by any filters beforehand. Why exactly this happens, why exactly it filters it by 50%, that will be discussed later. For now, we are only interested in what happens after the light has been thus polarized. Polarized light obeys Malus's law with respect to further polarizing filters. Malus's law encodes the observation that the intensity of a beam of light after passing through a second polarizing filter, call that I, the intensity of the beam of light, I, is a function of the intensity of the original beam, call that I null, times the difference in angle between the filters. The difference in angle is encoded mathematically in the expression cosine squared of theta. Thus, Malus's law is I equals I null times cosine squared of theta, i.e., the intensity of the beam is mitigated by the angle of the filter. For example, we pass a light beam with 100 units of intensity through a polarizing filter. This reduces it by 50%, or from 100 to 50 units of intensity. We pass this polarized beam through a second filter held at, say, a 27-degree angle relative to the first. The resultant intensity of the light will be 50 times cosine squared of 27 degrees, which equals 50 times about 0.79, which equals about 39.5 units of intensity. In other words, the light was reduced by a factor of about 21%. So that's all pretty neat, but what happens if we introduce a third filter? We'll call the first filter A, the second filter B, and the third and newest filter C. We know that filter A polarizes the light and reduces it by about 50%. Again, why it does this will be discussed later. What matters for us is that the light is now polarized, and it proceeds through filter B. The effect of filter B on the polarized light is dictated by Malus's law. Let's say that filter B is oriented at a 45-degree angle relative to filter A, so that it reduces the incoming light by another 50%. So, we started with 100 units of intensity, which was reduced by filter A to 50 units, and then by filter B to 25 units. What will filter C do? Filter C, as it turns out, will simply obey Malus's law. And the funny thing about Malus's law is that it only references the filter immediately previous to the current one. Thus, when calculating the effect of filter C on the light beam, we only need to know its angle relative to filter B, not to filter A. Filter A does not matter at all. So if filter C is oriented at 45 degrees relative to filter B, it will reduce the light by another 50% to 12.5 units of intensity. But note how strange this is, for if filter C is 45 degrees offset from filter B, and filter B is another 45 degrees offset from filter A, then filter C is a total of 90 degrees offset from filter A, which we established should mean that 0% of the light gets through, or 100% of the light is blocked, however you want to frame it. And indeed, if we remove filter B, so that we only have filters A and C at 90 degrees to each other, then instead of 12.5 units getting through, 0 units will get through. The opacity of these two filters is greater than the opacity of 3 filters combined. It is as if the filters, in addition to screening off the light, are actually altering the light so that the nature of the light passing from filter A to filter B is different from that passing from B to C. A curious consequence of this is that if you place more and more filters between A and C, so that each filter is offset by only a few degrees relative to the previous one, then more light will ultimately make it through to filter C than if the extra filters were not present. The extra filters seem to be guiding the light, easing its transition from 0 degrees to 90 degrees. What is going on here? As it turns out, polarization, just like interference, can be modeled with waves. Specifically, it can be modeled with transverse waves, that is, waves that propagate perpendicularly to their direction of motion. The simplest example is a wave rolling through a semi-taut string. The direction in which the wave moves is perpendicular to the wave's displacement of the string itself. The wave is an up-down displacement, you could say, rolling from right to left or left to right along a string. We can describe such a wave as being polarized, in the sense that it goes up and down in one set plane perpendicular to the direction of its motion. It thus has, in a sense, two poles, a peak and a trough, and an axis of polarization perpendicular to the axis of its motion, that is, the axis of the string. In contrast to this, one could imagine unpolarized transverse waves as not having a particular axis of polarization, but being a mixture of every possible axis at once. We can represent this, albeit somewhat misleadingly, by swinging the string around in a circle. Now it is polarized in every direction at once. In other words, it is unpolarized. Actually, what it really is circularly polarized, but for our purposes, either works. So we're going to treat it as unpolarized for visualizing it. So, what if our unpolarized string passes through a physical grating? As it turns out, something analogous to Malus's law occurs. The intensity of the waving in the string, here the amplitude of the wave, is cut down. Even more importantly, The string is now reduced to waving in a particular plane that matches the direction of the grating. It has become polarized. If we then place a second grating in the way and turn this grating 90 degrees relative to the first, then the wave will not be able to propagate beyond that point. But the closer we orient that grating to the first, the more the amplitude or intensity of the wave is preserved. So we can explain polarization using the basic mechanical principles of transverse waves. The trouble, of course, is that light is not simply a wave. We know it is made of particles, which, at least in interference experiments, produce wave-like effects in the aggregate. Can we recreate the effects of Malus's law using particles instead of waves? To get insight into this puzzle, let's leave light polarization for now and instead explore another quantum experiment which uses atoms of silver instead of photons. You can do it with plenty of other things, but when it was originally performed, it was atoms of silver. This is the Stern-Gerlach experiment, first conducted in 1922 by Otto Stern and Walter Gerlach. Take a lump of silver and seal it inside an oven. Poke a little pinhole in the side of the oven. Then cook the silver at 1,000,000,000 degrees so that it vaporizes into individual atoms of silver. These atoms will bounce around the oven until they finally escape through the pinhole in a fine beam. We have created a silver vapor gun. Now we can fight werewolves. We can also do the following. We can fire this beam of silver atoms through a funky-shaped pair of magnets. The odd shape of these two magnets is designed to create a non-uniform magnetic field. This just means that one of the magnets, the upper triangular one, has a stronger magnetic pole than the other magnet. In our experiment, the upper, stronger magnet has its north pole facing down towards the experiment, while the lower, weaker magnet has its south pole facing up towards the experiment. If we were to shoot a tiny bar magnet through this field, and if that bar magnet was oriented so that its north pole was up, facing the upper magnet, and its south pole was down, facing the lower magnet, then the upper and lower magnets would fight over repelling it, since in magnetism, like repels like. Now, if the magnets were shaped normally, so that their magnetic field was uniform, then neither the upper nor the lower magnet would win this struggle, and the little bar magnet would continue in a straight line between them. But because the field is non-uniform in favor of the upper magnet will always win, repelling the bar magnet down towards the lower magnet. In that case, the trajectory of the little bar magnet will resemble a cannonball returning to Earth. It curls downwards. On the other hand, when the little bar magnet is flipped so that its south pole is up while its north pole is down, now there is a fight to attract the bar magnet, a fight that the upper magnet will also always win, causing the little bar magnet to curl its trajectory upwards like a plane taking off from a runway. Now, it turns out that we can imagine the silver atoms in much the same way as little bar magnets with north and south poles. In other words, we can imagine our silver atoms as little pitted olives with toothpicks shoved through them. The toothpicks are colored blue on one side and red on the other to represent north and south poles respectively. Each olive, or silver atom, can be oriented any direction in space. If an atom is oriented so that its north pole is facing directly up and its south pole is facing directly down, we already know that it will be deflected down by the maximum amount allowed by the magnetic field. Likewise, if the atom is flipped around, it will be deflected up by the maximum amount. But what if an atom is oriented parallel to the magnetic field? Well, we would expect such an atom to not be deflected at all. It would just fly straight through. In fact, the amount by which each atom would supposedly be deflected should depend upon its orientation. The closer it is to pointing straight up or straight down, the more it will be deflected. The only other factor to note is that some atoms may stray more to the sides of the magnetic field. These will likewise experience less deflection because they are not under the full brunt of the field. Now we place a detector at the other end of the experiment so that we can see where each atom ultimately lands. And it seems like we should expect an oval-shaped blotch to form there. The atoms pointing directly up and down would form the uppermost and lowermost bounds of this shape, while the atoms pointing parallel to the magnet would form the midline, and all the other angles would fill in the gaps. Furthermore, as we go further to the right or left of the main field, the atoms are less and less deflected, so that the shape closes off at the edges, making something shaped more or less like an eye. But that is not what we get. An eye-like shape will form, but it is not filled in. We only see the uppermost and lowermost bounds of the eye, no midline, no in-between. There's an empty space there. This means that every silver atom is deflected up or down by the maximum amount allowed by the magnetic field on its trajectory. Well, wait a minute. Maybe by some freak accident something is up with our silver beam. Maybe the pinhole in the oven is somehow affecting the silver atoms, so that by a crazy coincidence they come out maximally polarized, note that word, polarized along the same axis that we happened to choose for our Stern-Gerlach magnets. Well, we can easily check this by simply rotating the Stern-Gerlach magnets by 90 degrees. Now, the allegedly polarized atoms shouldn't be deflected at all. They are parallel to the new orientation. Yet deflected they are, now at a 90-degree angle to match the magnets, so that now we have an eye turned on its side. And this is the case no matter how we orient the Stern-Gerlach magnets. If we wanted, we could continuously spin the magnets around and turn our silver beam into a weird spiraling series of eye shapes or something. From all of this, we can conclude that the Stern-Gerlach magnets are not passive devices. They are changing the nature of the silver beam. Specifically, they are separating the silver atoms into two camps, those repelled down from the upper magnet and those attracted up towards the upper magnet. These options are called spin down and spin up, respectively. The word spin, by the way, it's a bit confusing, but fortunately it's not really important for our purposes. That's just a whole can of worms that we don't have time for. So, sorry if that's confusing, but we are going to use that term spin. How do we make sense of all of this? Well, perhaps it is the case that, with individual atoms of silver, a magnetic field of any measurable strength does not simply deflect them, but actually causes them to reorient themselves, that is, to line up with the field they are exposed to. An atom whose south pole is already angled somewhat downwards will be pushed all the way downwards, and an atom with its south pole angled upwards will be pushed all the way upwards. In other words, the Stern-Gerlach magnets radicalize the silver atoms, exploiting even the slightest pre-existing tendency in one direction or the other. Well, we can actually test this theory. Instead of catching the silver atoms on a detector, let's redirect the spin-up half of the silver beam into another Stern-Gerlach setup. And let's have this other Stern-Gerlach setup oriented at the same angle as the first. Much like the polarizing filters, we placed filter B after filter A, but at the same angle. So, there is a 0-degree difference between the angle of the first pair of magnets and the angle of the second pair. If our theory is correct, namely that the magnets are radicalizing the pre-existing tendencies of the atoms, then we should expect our spin-up beam to remain 100% spin-up in the second one. The second pair of magnets will simply reinforce what the first pair of magnets did. And indeed, that is what we see. We get only the upper bound of the eye, not the lower bound. 100% of the atoms remained the maximal amount spin up when passed through the second set of magnets. But what happens if we rotate that second pair of magnets just as we did with the polarizing filter, so that there is a difference between the angle of the first pair and the angle of the second pair? For example, let's rotate the second pair of magnets to a 90-degree angle from the first pair. This gives us an interesting situation. Relative to the first pair of magnets, our spin-up atoms are pointed directly up, but relative to the second pair of magnets, these same spin-up atoms are now pointed parallel to the magnets. In other words, relative to the second pair of magnets, our silver beam has no pre-existing tendency to flip one way or the other. Technically, this was already a possibility with the first pair of magnets because who knows what polarizations of silver atoms we were getting, but now we have to face this possibility head on. What happens now? As it turns out, the beam will split 50-50 again, just as happened with the first magnet. Half of the atoms will deflect towards the stronger or upper magnet, and half will deflect away from it. It's a coin toss. Interesting. But we could still say that, practically speaking, every atom has a pre-existing tendency one way or the other. It's not realistic to assume that our spin-up beam of atoms are all perfectly spin up. Surely there is some wiggle room there for our 90-degree magnets to exploit. And the number of atoms that really are perfectly balanced between both magnets must be so minuscule that we could not distinguish their detection from experimental error or background noise. Well, what if we only offset the second magnet pair by 45 degrees instead of by the full 90? In that case, should we not expect 100% of the spin-up atoms to be deflected spin-up once again? Granted, they are not perfectly aligned with the previous magnets, nevertheless, they are all still angled such that flipping to up at 45 degrees will be far easier than flipping back the other way around towards down. The atoms have been primed by the first set of magnets to be spin up in the second pair. But this is not what happens. At a 45-degree angle, only 85% will be deflected up like before. The remaining 15% will be deflected down. What about at a 60-degree angle? 75% up, 25% down. What about a 75-degree angle? Now it's 63% up, 47% down. Then, at last, we reach 90 degrees again, where it is 50% up and 50% down. How very strange this is. Imagined Pictorially, it seems as though some of the atoms take the more difficult path, swiveling themselves a full 135 degrees around. Remember, we found something similar in the double-slit experiment, where the photons would have to swerve around barriers in non-Newtonian ways. At first glance, this would seem to be a violation of the conservation of energy. Where is the energy coming from for the particles to take anything other than the path of least effort? And what determines which atoms will flip around in this way in the first place? The most constant aspect of the Stern-Gerlach experiment is the percentages. Given a 45-degree angle, 85% of the particles will stay up, while 15% will switch to down, and God only knows which particles will make which choice, for there appears to be no mechanical reason whatsoever for a particle to switch like that. Now, as it turns out, the percentages can be predicted with a neat and rather familiar formula. The percentage of atoms that will be deflected up by the second pair of magnets is equal to the squared cosine of half the angle between the first pair of magnets and the second. In other words, the probability of up equals cosine squared of half of theta. This, of course, is very similar to Malus's law. The chief difference is that while Malus's law multiplies the squared cosine by the intensity of the original beam, this new version simply takes the squared cosine of half the angle. But these changes are not all that significant for our purposes. They simply reflect variations in the practical aspects of each experiment, not the underlying principle, which is ultimately represented by the squared cosine itself. This similarity is one of the reasons for considering the polarization experiment along the same lines as the Stern-Gerlach experiment. Each photon is said to have its own pre-existing angle of polarization, its own toothpick, if you will, which is radicalized by the electromagnetic fields present in the polarizing filter. If the beam of photons is unpolarized, meaning it has a random distribution of polarization angles, then the filter will absorb 1/2 of the photons on average, and let the other half alone. Meanwhile, the Stern-Gerlach experiment lets both halves pass through, only sorting them into two different beams. It is this change, this reification in the beam caused by the filter, that allows more light to pass through 3 oblique filters than would pass through 2 perpendicular filters. But again, note the cost of this explanation, the potential violation of energy conservation through the apparently spontaneous and groundless enforcement of a strict statistical law. We now have particles suddenly deciding to move in weird ways just to satisfy an arbitrary quota imposed from above. This unsettling consequence is usually resolved by treating the system as a black box and saying, the quantum realm is weird, don't think about it. But perhaps there is another way around all this. Could it be that, in addition to polarization or spin, there are other hidden variables which account for the behavior of quantum particles? For instance, perhaps the other angles at which a particle is polarized play a hitherto unrecognized role. Or maybe there is something to do with the torque of the particle as it literally spins. Or maybe there's some kind of strange Brownian motion going on where stray particles from who knows where hit our particles and cause them to flip around. The sky is the limit, really. The key assumption here is that the outcome of an experiment works like a kind of mechanical equation, where you plug certain inputs into a function and get certain predetermined outputs. Consequently, if you know the function, then knowing the inputs is the same as knowing the outputs, and vice versa. There is a predetermined correspondence between inputs and outputs via the function. For instance, if we plug the number 3 into the term x plus 6, we know we will get 9 as an output. If we found that we only sometimes get 9 as an output, we would not conclude that the equation is probabilistic, but only that we are bad at math. Or if we cannot find any mathematical errors, then we must instead assume that we are putting in two different inputs, but calling them both 3. In other words, there is something about our inputs, some hidden variable, some, as it were, hidden decimal place that results in our seemingly probabilistic answers. The point is, there must be a mechanical reason that we get one answer versus another. We are thus justified in saying, for instance, that if an incoming particle is polarized at 45 degrees from the x-axis, 15 degrees from the y-axis, and 120 degrees from the z-axis, then we can know with certainty how it will behave if passed through, say, a Stern-Gerlach angled at 30 degrees from the y-axis, followed by a Stern-Gerlach angled at 75 degrees along the y-axis. The hidden variables in this case would be the particle's angle of polarization along the x and z axes, which, for all we know, contribute to the scenario in some way. There could be some other variables at work too, but the point is, if we know all the relevant inputs, we know the output already. Past and future are bound together by an iron chain, the function of the laws of nature. But ironically, quantum mechanics does not give us such a function on the level of the individual particles, but only on the macroscopic level of the entire beam. Quantum mechanics cannot tell you with certainty what will happen to any individual particle when it passes through a polarization filter or a Stern-Gerlach apparatus. It can only give you certain probabilities. This is the point made by the uncertainty principle. When you are dealing with single particles, there is irremediable variation between the outcomes of different experimental trials, no matter how precise your equipment is. What this seems to break is any strict cause and effect on the level of individual particles. When we ask for the reason that this or that silver atom swiveled 135 degrees around, quantum mechanics cannot give us an answer, except in terms of the entire beam. There wasn't anything special about that atom, according to quantum mechanics. It just happened to be one of the atoms that fulfilled the quota. There was no reason for it to swivel like that on the level of the individual atom. There was only a reason at the level of the entire beam. Insofar as quantum mechanics refuses to explain why the individual particles do what they do in a given scenario, i.e., insofar as quantum mechanics is microscopically indeterministic, it is by way of compensation macroscopically deterministic. The strict function of input and output is not given at the level of the particles, but at the level of the entire beam and apparatus. The behavior of the beam is not an emergent property of the determined motions of its parts. Rather, if anything, the behavior of the parts is an emergent property of the motion of the whole beam. The whole determines the parts, not vice versa. But are we committed to this, or to anything like it? Do we really have to say that the individual particles are indeterministic in this way, or is it not rather more likely that quantum mechanics is simply leaving something out? Is there some way to salvage the old microscopically deterministic picture?